Hello, chemistry class, and right now we are looking at geometric structure of molecules. So this is the last section of this unit, and it is talking about the shape that different molecules take. And here I've just shown a few examples of some different molecules, and you certainly don't need to know all these or memorize them. I just wanted you to get an idea in your head that molecules can take a lot of different shapes. These are fairly simple molecules, and each one has its own interesting geometrical three-dimensional shape. Now, when we predict how a molecule will be shaped, what its structure is going to be, we use something called Vsepr theory. It's valence shell electron pair repulsion. And it's based on the idea that electrons in a molecule they repulse each other. They want to be as far apart from each other as possible. And in Vsepr theory, we are going to minimize the repulsion between the electrons in order to find its molecular structure. So let's take a look at water. Here we have the Lewis structure of water. Oxygen has two lone pair of electrons, and here they are represented in its three-dimensional structure. It also has two bonded pair. One is bonded to hydrogen and the other is bonded to another hydrogen. All of those electron pairs are important in determining its structure because all of those electron pairs want to be as far away from each other as possible. In order to accomplish this, this entire molecule is going to take the shape of a tetrahedron or a tetrahedral shape in order to maximize its ability to keep these electron pairs far away from each other. Now, the interesting thing is that even though this is the shape of water with its lone pair electrons, that is not the final shape of the molecule. The final shape of the molecule is only including the hydrogen, the oxygen, and the other hydrogen. So it has the fancy name of bent. That's its shape. So oxygen bonded to two hydrogens, water, is always in a bent shape, and this angle is always 104.5 degrees, and that is the shape that water takes. So how do we predict the shape of any given molecule? Here are some rules that will help us to do that with our Vsepr theory. Number one, we draw the Lewis structure. So here's an example. I picked methane. It's a fairly simple molecule. Here's the Lewis structure of methane, and then step two, we count all the electron pairs, bonded and unbonded, and we arrange them to minimize repulsion. So in this case, we only have bonded pairs. They're 1, 2, 3, and 4. And when they are arranged to minimize the repulsion, the shape is tetrahedral right here. That's the shape that we can have each of these pairs of electrons as far apart from one another as possible. Then we find the positions of the atoms, which we have right here, and we name the molecule based on the positions of the atoms, not on lone pairs. And this doesn't really affect us in this case because we don't have any lone pair electrons. So our final shape is tetrahedral. What if there are lone pair electrons? Let's do an example with lone pair electrons. The example we're going to look at is ammonia. And here, if we have an ammonia molecule, we're going to first, remember, draw the Lewis structure. Here's our Lewis structure. Second, count all the electron pairs bonded and unbonded and arrange them to minimize repulsion. So we have 1, 2, 3 bonded pair, and we write these in. Here's our nitrogen with 1, 2, 3 bonded pair, and 1 lone pair of electrons. So that's up here, our lone pair. And we have a tetrahedral shape when we're talking about all of the electrons involved. However, the very last step, we're going to find the position of the atoms and name the molecule based on position of the atoms, not the lone pair electrons. So when we look at only the atoms, right here, they are going to be in this shape. This shape is called trigonal pyramidal. And the reason we have this shape is because there is a lone pair of electrons right here that is causing these hydrogens to be in those positions so that all of the electron pairs, bonded and non-bonded, are far away from each other. So the final molecular geometry of ammonia is trigonal pyramidal. So what are some of these other possibilities? There are actually more geometric shapes and possibilities than these listed here, but these are the ones that we're going to work with in our class and as we're studying this. So we have a linear geometry where there's 180 degrees between the two atoms on the ends, and an example of that would be carbon dioxide. We have a trigonal planar geometry, and there's 120 degrees here in the angles between those atoms. Boron trifluoride is an example of that. Here is a tetrahedral shape of geometry, and here is the angle, the degrees between the angles there. Methane is tetrahedral, and we looked at that already. Here is a shape that is tetrahedral in its electron group geometry, but it's trigonal pyramidal in its molecular geometry. So when we talk about the molecule itself, the molecule is trigonal planar, but when we're talking about all of the different electron pairs, it's tetrahedral. And we just looked at the ammonia atom or molecule, and that was in this category. Here's another example that falls into that category as well. We also have an example of tetrahedral where two of the branches on the tetrahedron are lone pair, and then the molecule, the molecular shape, actually ends up being bent. And if you'll remember, water was an example of that because it had the two electron pairs. So for some advanced proficiency, if you'd like to go above and beyond and research this a little more, you can look at how you would determine a Vsepr, follow the Vsepr rules for determining structure when a double bond is involved in the molecule, because we haven't talked about that. You could research how you would account for resonance structures. Those two questions go together a little bit. And you could give examples of molecules that have different geometric structures than the ones that we have talked about in the last slide. There are a variety of larger molecules that have more bonds than these and have some different shapes. So those are some wonderful things that you could look into and find out a little bit more how molecules form their geometric shapes.